All right, so in this video, we're going to take a look at recognizing different types of organic acids and bases. So a couple of things that we want to keep in mind as you go through some of these questions. So this kind of goes back to what we learned in one of the earlier weeks when we looked at the differences between acids and bases. Right, acids are things that donate or lose protons or H pluses. Bases are things that accept H pluses. In organic chemistry, our acids are usually things like carboxylic acids, which have the carboxylic acid functional group that looks like this, right? And this fourth bond here is to the rest of the molecule, which we designate with R. This is the proton or the H plus that can be lost. Your bases typically tend to be, there can be several different varieties, but they tend to be amines, and those are the most common examples that we'll see. And amines kind of look like this. So you have your nitrogen that's connected to a couple H's or maybe one H, and then the third bond here is to the rest of the molecule. This can accept or it can gain an H plus. And if that gains an H plus, we end up with R. We now have three H's, and now there's a positive charge on the nitrogen. When the acid loses a proton, we get rid of this H plus over here, we end up with R, C double bond O, and then O with a minus charge, right? So that's the basis for understanding these types of questions. Now, when we're given our options here, so it says correct each molecule to sort structure that it would have if it were dissolved in a 0.1 molar aqueous solution of sodium hydroxide, right? So a couple of things we need to note here, NaOH, that's sodium hydroxide. We've seen that before several times in this class. Sodium hydroxide is a base. So if you react it with something else, that something else would react as an acid. So when you look at our options that we have here, so we have two different molecules. We'll take a look at the first one. This first one actually is an acid, right? Because it contains the carboxylic acid functional group. This can then lose that H plus. And if it loses the H plus, right, we lose the H plus from the carboxylic acid side of it over here, not the OH from the hydroxyl side. All right, so you want to pay close attention to that. It's the carboxylic acid part of the molecule that will react. So when you draw your structure, all you need to do is to draw the original structure, but then just remove the H plus from it, and you end up with this O with a negative charge. You'll notice that down here, nothing happens to this OH because that's not part of a carboxylic acid functional group. Okay, so now we're going to take a look at recognizing and drawing primary, secondary, and tertiary amines. Okay, and amines are all going to look similar to each other. There's a nitrogen that's central to it. Primary amines are going to have a nitrogen connected to just one other carbon directly. Secondary amines are going to have a nitrogen connected to two other carbons. And then tertiary amines will have a nitrogen connected to three other carbons, right? So we'll designate those carbons with the letter R. That just means the rest of it has carbons in them. So if you're asked to draw the condensed structure of a primary amine with three carbons and no double or triple bonds, okay, then a primary amine will look something like that. So we have our NH2, and then we have how many carbons? 3. So we have our CH2 that's in the middle, CH2, and then our CH3 at the end, right? So our R group here, the remainder of this molecule is this entire thing. We have 3 carbons, the correct number of hydrogens, No double or triple bonds. This is primary because the nitrogen is directly connected to just one other carbon. And so when you draw your structure, all right, so we need our carbon first, and then we have a bond to another carbon. That's a CH2. That's bonded to another CH2. And then at the end, we have our, what is that, our NH2 at the end. We'll change the first one here to a CH3. And let's see if that works. Most likely it's not, because remember now, this actually needs to be a H3C to show the correct connectivity. So if I check it, we can see that it is correct. All right, so as you go through, you want to make sure that you know what primary versus secondary versus tertiary mean. Draw it out on a sheet of paper and then transfer it over to the template. All right, so now we're taking a look at drawing and naming and drawing primary amines that don't have any side groups attached to them. Okay, and so we have here 1, 2, 5 hexane triamine. Okay, and the good thing about organic nomenclature is that you're told exactly everything you need to know about the structure from the name. And you always start with the last name first. All right, so we know this is an amine, so it's going to have that nitrogen, but we have 3. The tri, that means 3 amino groups in it, and our main carbon chain here is hexane. So we have 6 carbons in a row. That's what the hex means. So 1, 2, 3, 4, 5, 6. And our 3 amines are on carbons 1, 2, and 5, right? So I have the, I can select to number this whichever direction I want. So I'm going to go from the left to right. So 1, 2, 3, 4, 5, and 6. I have an amino group on carbon 1. That's our NH2. I have an amino group on carbon 2, NH2. I have an amino group on carbon 5, NH2, and I'm just going to fill in the remaining bonds to the carbons to make sure the carbons have the correct number of bonds and hydrogens connected to them. All right, so there's my structure. I'm going to convert it now to the our ALEKS. So you have a CH2 that's connected to another C that's connected to a third one, which is a CH2. Fourth one, which is a CH2. Fifth one, that's a CH. And then the sixth one is a CH3. And I'm going to fill in now, there's a bond here to an NH2 on carbon number 2. This should be a CH2 here. I'm sorry, a CH. The bond down to an amino group, NH2. And then at the end, I have another NH2 there as well. All right, so if we check that, there's your structure. So start with the name, start with the last part of the name. It tells you the longest carbon chain, the functional groups present. The numbers tell you where to attach the functional groups. All right, now we're going to take a look at naming aldehydes and carboxylic acid. So when it comes to naming these, you want to make sure that you identify what family they belong to first. Okay, so remember now your carboxylic acid is going to have the C double bond O connected to the OH, whereas your aldehyde also has the C double bond O, but then that's connected to an H, right? So they look very similar, but they're actually different, and they have different properties. All right, let's take a look at the first one. So we have our double bond, C double bond O. I have an OH over here, a CH, CH3, and then a CH2, and then a CH3. All right, so the first thing we need to do is identify the functional group, and there's our functional group. So it is it's a carboxylic acid. And when it comes to naming or identifying the longest carbon chain, that has to be your carbon number 1, right? We want to number the chain to give the lowest number possible to that carbon, and then we're going to just follow this along to get the longest continuous carbon chain, which in this case is 4, right? So the carbon of the carboxylic acid is part of the longest chain. So our longest group here is 4, longest carbon chain is 4, so that's bute. This is a carboxylic acid, so it would end in butanoic acid. And then there's a methyl group on carbon number 2, so that would be 2-methyl butanoic acid. So you want to approach your naming here systematically so that you follow all the rules. For the second one, we have our CH2 connected to the O. All right, if you expand this out, it's a little bit easier to see that this actually looks like this. We have your C double bond O, the 2 H's to the side. Okay, there's your aldehyde group. So this then would be an aldehyde. There's 1 carbon in it. The prefix for 1 is meth. All aldehydes are going to end in that ending. That would be methanal. And then the third one actually is the same thing. You see double bond O connected to those H's, just a different way to represent our structure. Right, so we have 2-methyl butanoic acid. Remember the methyl and the butanoic, they're one word, then there's a space between the ic and the acid. We have methanol in 2 different, or represented 2 different ways. All right, now we're going to take a look at drawing and naming, or at least naming carboxylic acids. So we're given here now the structures, and we need to come up with the name. All right, and this is all about what nomenclature is, going back and forth between the structures and the names of things. So we have this as our structure. So identify the functional group. So there's our carboxylic acid. The carbon of the carboxylic acid has to be part of the longest chain, and we just find the longest continuous chain, which would be this. All right, so we have that'll be our carbon 1, and then we just continue all the way across 2, 3, 4, and 5. So 5 is our longest chain. That's pentan. The carboxylic acid would mean that it ends in oic acid, so pentanoic acid. On carbon 2, we have a methyl. Okay, so this here would be 2-methyl. And then we have a OH on carbon 4 and an OH on carbon 5. So the OH, when they're groups, they're called hydroxy. And they're on carbons 4 and 5. So 4,5 dash hydroxy. And then we have our 2-methyl. We're going to put those in alphabetically. So the 4,5 dash hydroxy goes first. And then dash 2 dash methyl. And then pentanoic acid, all one word here at the end, with a space between the pentanoic and the acid. All right, so as you name it, there's one thing to note about the name, because we have 2 hydroxy groups. Okay, we actually do need the prefix di for dihydroxy in the name, and we'll include that here as well. All right, so 4,5 dash dihydroxy for 2 hydroxyl groups, and then our 2-methyl pentanoic acid. All right, now we're going to take a look at how we name esters. All right, so if we have, we'll do the first one, CH3OCOO, or CO, and then CH2, CH3. All right, so this all starts with identifying the functional group. And hopefully you can see now you have your C double bond O that's connected to carbons on either side. So this here, you need to pick that out from the lineup. That is your ester functional group. So we're going to name it as the ester, right? So the way that we want to orient ourselves is you find the C double bond O, and then we're going to draw a line right between the C double bond O and the O right next to it. And we can tell from this which part of the ester came from the acid. The C double bond O part came from the carboxylic acid, and then the other side of it came from the alcohol, right? That's how you can identify the different fragments of your ester. So when you name the ester, the first name from the ester comes from the alcohol that was used. This is a 1-carbon alcohol, so we call that methyl, meth for one, and il for the ending. And the second name for the ester comes from the carboxylic acid. This is a 3-carbon carboxylic acid, so a 3-carbon would be prop, and then we change the ending to anoate. So this will be methyl propanoate, right? And just to clarify where these two came from, methyl came from the alcohol methanol, and then propanoate came from the acid propanoic acid. Okay, so when you're given the structure, identify what family it belongs to by locating the functional group, and then we're going to use the rules for nomenclature to come up with the first name and then the last name. First name comes from the alcohol, last name comes from the acid. All right, so now we're going to take a look at predicting either the products or the reactants for an esterification reaction. Okay, so esterification is nothing more than the process of making an ester. And you can tell that we're making an ester due to a couple of things. We can tell from the reactants. So we have here an acid and an alcohol. We can also tell from the conditions. We have an acid catalyst and we have heat. So what we need to do is to draw the product, specifically the condensed structure of the product P that we get. In an esterification reaction, we also produce water as one of the products. All right, so let's draw out the structures of the reactants. Okay, so I have my acid and I have the alcohol. So what's going to react here are the carboxylic acid part of the acid and the alcohol part of the carboxylic acid part of the acid and the hydroxyl part of the alcohol are the things that are going to react. So when I draw them out, I can actually draw those parts that are closest to each other. That way it's going to be a little bit easier to see the changes that are occurring. All right, so I end up losing the OH from the acid, and I end up losing the H from the alcohol. These combine to give me my H2O. Okay, and all I'm going to do then is to connect this C double bond O that I have. I'm going to connect that with this O over here. Okay, so that's the O, and then this O brings with it from the alcohol everything else it's connected to. So this O is connected to a CH, that CH is connected to a CH3, and another CH3. All right, so this part here came from the alcohol, and then the left part came from the acid, which is this part over here. We lost the part in purple, which is the water molecule, right? So that's your ester that you make. We can tell it's an ester because we have the ester functional group. We just need to go ahead and transfer this over to the ALEKS template. All right, so let's take a look now at hydrolysis of esters. Okay, which is simply taking an ester and breaking it down. This can happen under a couple different conditions. So I have here the first the ester to begin with, and then I'm told that I have NaOH, and I'm going to use some heat to cause this reaction. So this here tells us that this is hydrolysis under basic conditions. Okay, and when you hydrolyze an ester, we're always going to break the bond that was used to connect the acid and alcohol in the first place. So we're going to break this right down the middle here. Okay, so you find the ester functional group, and then we're going to split it right between the carbonyl, C double bond O, and that O. And we can then draw the fragments that result. So on the left side of this, I have my C double bond O, and that's connected to these other carbons. On the right side, I have my O that's connected to 3 other carbons. So how do we complete the product? Well, I'm going to now take my NaOH and I'm going to combine it with the fragments in this way. The H here from the NaOH goes and it completes the original alcohol. And then the Na and the O, they go in here and they complete the acid fragment. Specifically, the O gets connected as an O minus, and then the Na gets attached as an Na plus. So we end up making this salt, or this ionic compound. We call it the salt of the carboxylic acid that we make as a result of, in this case, basic hydrolysis of an ester, which is also known as saponification. Okay, so when you hydrolyze it, whether it's basic or acidic conditions, locate the ester functional group. We're going to break it right immediately between the C double bond O and the oxygen adjacent to it. We're going to get our fragments, and then we're going to complete those fragments based on the types of conditions that we're working with. All right, so we have our products drawn here, which are the same products that we have written out on our sheet of paper. All right, and now we're going to take a look at amidation reactions. So these are very similar to esterification. Esterification is just making an ester. Amidation means making amides. And typically, to make an amide, we're going to need a carboxylic acid reacting with an amine. Right, those are the most two common ingredients to make an amide. So I have here my amine that's written out. I have CH3, NH, CH3, and then reacting with my carboxylic acid, C double bond O, OH, and then that's connected to a CH2, CH3. So just like with the esterification, try to identify the parts of each of these 2 molecules that are going to react. So what I did was I actually expanded out the amine structure to show that hydrogen connected to the H, because that's the hydrogen that is going to react with now the OH from the acid. These 2, as you can imagine, react together to give you H2O as one of the products. And all we're going to do now is to connect the remaining 2 fragments together. So this part of the carboxylic acid gets connected to the amine via this nitrogen right here. So that's going to connect to that C double bond O. So if I draw the product, right, I can draw everything that doesn't change. So I'm going to move the CH3 up here a little bit. So I still have my 2 CH3s connected to the nitrogen. That hasn't changed. There's my nitrogen. Now the 3rd bond is not to an H anymore. Now it's to this C double bond O. That comes from the acid. And then that brings with it a CH2 and a CH3. And that's your amide. We can tell it's an amide because we have the amide functional group, the carbonyl connected to that nitrogen. All right, so here you have your product drawn. There's a C double bond ON. It looks just like the one that we drew on the paper, but it's just flipped around. It's the exact same molecule. All right, so now we're going to take a look at amide hydrolysis. All right, so amide hydrolysis is where we're going to take an amide and we're going to break it down. And just like with ester hydrolysis, this can happen under acidic or basic conditions. So we need, obviously, the amide bond to be present to break it down, and we're going to split it right after the C double bond O, just like we did with the esters. All right, so if you look here at the questions that are given, or the question that's given, we actually don't have an amide to begin with, but we do have a carboxylic acid and we have a potassium hydroxide. So this is the base, and that's an acid. So this is actually an acid-base reaction. It's not an amide hydrolysis reaction. So because this is an acid-base reaction, we're going to end up making a salt and water. Just like in any acid-base reaction, we're going to do just write out the parts of the molecule that don't change. So I have my acid here, carboxylic acid, and I have my potassium hydroxide. So acid and base, right? We usually react to produce a salt and water. So the acid is going to give up its H plus, and the base is going to give up its hydroxide, its OH minus. These are going to combine to give you H2O, right? The H here and the OH, the H plus specifically and the OH minus. So what we end up with then is this carboxylic acid losing its H plus. So that'll have then, we took away this H plus here. So this O that remains is going to have a negative charge. And then the potassium hydroxide, we lost the OH minus, we're left with a K plus. And those two opposite charges simply associate with each other. This is your salt that ends up being made. All right, and here we have another one that's showing amide hydrolysis specifically. So we have our molecule to begin with. We have our conditions, we have H2O, we have HCl, and then we have heat. The triangle means heat. All right, so identify the functional groups that are important. So here we have our amide functional group right there. And then the conditions are going to be important. So we have HCl, that's hydrochloric acid. Okay, this would be acidic hydrolysis that we're looking at. And when we're going to hydrolyze this amide, we're going to split it right between the C double bond O and the nitrogen, right? So that's the amide bond that we have highlighted, and then we're going to break it right between those two parts. So we're going to end up with two fragments now. So I'm just going to draw those fragments, the parts that don't change, right? And this is the way that you want to approach these. So they are the two fragments that I end up with. Now, what we need to do is to figure out, well, under acidic hydrolysis, what products do we actually get? So under acidic conditions for hydrolysis, what we end up with is we get back the original carboxylic acid. And then we also get the salt of the amine. Okay, so where does that actually come from? Well, if you think about your H2O here, right, your H2O is made up of an H and an OH, right? So the OH comes in and it completes the carboxylic acid side of things. Remember, it goes in as an OH minus. The H comes in here to give us then to complete the amine, but then we also have hydrochloric acid that is giving us an H plus that's going to give our nitrogen a positive charge, right? So this H comes in here as well, that one, as well as the one from the HCl to give us the NH3 plus. At the end of the other fragment, we also have the Cl minus that's floating around to neutralize that charge, right? So we end up with, let me redraw these. We end up with the original carboxylic acid, and then we get the salt here of the amine, right? So we have an N, we have 3 H's attached to it, the positive charge, and we have our Cl minus that's floating around. Sometimes the Cl minus is shown in, sometimes it's not. In this case, all we have here is the NH3 with the positive charge.